I'm Masayuki Fukumitsu from Hokkaido Information University, Japan. The title of our talk is A Tightly Secure DDH-based multisignature with Public Key PK Aggregation. This is a joint work with Shingo Hasegawa from Tohoku University, Japan. Our main topic is the multisignature schemes. A multisignature schemes is one of the specific types of digital signature schemes in a sense that it enables a group of multi-signers to issue a signature of a message. Recently, this is employed in the blockchain to support a transaction by multiple users rather than the individual one. Namely, the multi-signature schemes enable us to compress the size of signature in a transaction. We consider that the multiple users want to make a transaction. In the case where an ordinary signature scheme is employed, all users are required to sign the transaction. Therefore, the number of signatures are the same as that of users like this. On the other hand, the number is reduced to only one when a multi-signature scheme is employed. Moreover, since the public keys are written as the addresses in the blockchain of Bitcoin system, it is desirable as to compress not only the number of signatures, but also that of public keys. Multi-signature schemes which have public key PK aggregation realize such compression. PK aggregation means that it enables us to compress public keys of involving signers to a single aggregated public key. Namely, this can aggregate all signers' public keys to one public key. So, by the multi-signature schemes with PK aggregation, we realize that the data size of the address and the signature is independent of the number of signers. In this slide, we collect the conventional multi-signature schemes with PK aggregation. Observe that the security of all of them was proven by root reductions. Let us explain the meanings of root security and tight security. These are related to the fraction L of this inequality between the success probability of security reduction R and that of a forger F. We say that security reduction R is loose if such a parameter L is a polynomial in security parameter, whereas it is said to be tight if such a parameter L is constant. In this sense, tight security guarantees that the security level of a cryptographic protocol is the same as that of the underlying cryptographic assumption. So, the tight security is desirable. However, there is no tightly secure multi-signature schemes with PK aggregation so far. In fact, all tightly secure multi-signature schemes do not support PK aggregation. So, in this talk, we address the question whether or not one can construct a tightly secure multi-signature scheme with PK aggregation. In this talk, we propose the first tightly secure multi-signature scheme with PK aggregation. The construction of our proposed schemes is almost the same as that of Lee, Yang, and Gorbani LYG multi-signature schemes. And the idea of the security proof is followed by that of Lee, Bonekes, and Gabiron LPG tightly secure multi-signature schemes. By combining them, our proposed schemes is proven to be secure under the DDH assumption in the random walkout model with respect to the plain public key model. The plain public key model is one of the security model which has no assumption on the key generation. Since our construction is almost the same as LYG construction, the features are the same as them, except that ours only achieves a tight security. This is our main point. This is the agenda of our talk. We briefly recall the definition of multi-signature schemes with PK aggregation and the plain public key model. And then we introduce our proposed schemes and show the tight security of our proposed scheme. A multi-signature schemes with PK aggregation consists of the 6 algorithms. The first one is the setup algorithm. The setup algorithm generates a public parameter. By using this, each signer generates a pair of a secret key and its public key. A multi-signature can be issued by the designated signing protocol. To run this protocol, each signer executes the signing algorithm. Then, the signer's public key can be aggregated by key aggregation algorithm. The validation of the aggregated public key can be checked by the verification algorithm. Finally, the validation of signatures can be checked by this verification algorithm. We now introduce the security in the plain public key model. This is defined by the security game between the challenger and the forger like this. In init phase, challenger generates the public parameter and the target public key, and then sends it to the forger. In sign phase, a forger queries a message and public key set. For each query, the challenger computes the signature as an answer. Finally, forger outputs a tuple of a public key set, a message, and a forked signature. The forger is said to be win this game if these conditions hold. We now introduce the proposed multi-signature scheme. This slide shows the setup, key generation, key aggregation, and its verification algorithms. We have 2 main points. The first one is that a public key is a random DDH pair. The second one is that an aggregated public key made from each of the public key and the hash values. This setting is followed by LYG construction. This is the signing protocol of our proposed scheme. Intuitively, a multi-signature is made by the protection of the KW signature generated by all of signers. It should be noted that the difference from LYG schemes is the broadcasted value in the first round. In fact, each signer broadcasts the 1 hash value in our proposed scheme. On the other hand, in their schemes, each signer hashes each of elements in commitment pair, and hence the 2 hash values are required to be broadcasted. So, our proposed schemes reduces the size of the communicated value. This is a verification algorithm. The verification formula is the production of that of KW signature scheme. We would like to move on to the security proof of the proposed scheme. This slide shows the statement of our main theorem. Assume that DDH assumption holds, then the proposed multi-signature scheme is tightly secure in the plain public key model with respect to the random oracle model. In fact, this equation shows that the proposed scheme is tightly secure. We briefly show the proof. The proof consists of three steps according to LPG and KW strategies. So we first replace the sign phase in PPK game with the simulator. The signing oracle simulator does not use secret key. We next switch the challenge public key into the random pair from the DDH pair. It should be noted that such a switch is indistinguishable under the DDH assumption. We finally evaluate the winning probability of the changed PPK game. In particular, we show that such a probability is negligible. We showed the signing simulation. Recall that the multi-signature of our proposed scheme is production of KW signature generated by each signer. So, our simulator is required to generate his part. This can be done by utilizing the honest verifier zero knowledge of KW signature scheme. We explain how to show that the winning probability of the changed PPK game by F is negligible. The main idea is followed by the original KW signature scheme. They evaluated the probability by the fact that the switched public key is non-DDH pair. So, we show the probability by proving that the aggregated public key is non-DDH pair. Therefore, the proof can be done in the same way as KW signature scheme. Please refer our proceeding for more detail. Let us summarize our main points. In this talk, we have proposed the first tightly secure multi-signature scheme with public key PK aggregation. Our construction is almost the same as that of LYG multi-signature scheme. Moreover, the security proof is followed by that of LPG tightly secure multi-signature scheme. So, our proposed scheme achieves tight security in random oracle model with respect to the plain public key model under the DDH assumption. We finally present our future works. We have two future works. The first one is to apply our approach to the other multi-signature schemes. For candidates, we consider the lattice-based one and the round optimal one. In particular, these lattice-based multi-signature schemes use the same technique to prove the security. So, we will attempt this work. The second one is to construct a generic construction of tightly secure multi-signature schemes with PK aggregation by using our approach. Thank you very much for your kind attention.